Hi everyone, my name is Shishir Adhikari and our team consisting of Prashesh Adhikari, Siddhanta Adhikari, Pratik Pokhrel and Kasmik Regmi are going to talk about edge computing. In this presentation, we'll first explain what edge computing is, then I'll compare it with cloud computing, share an analogy to make it easier to understand, and finally show you some real-world applications, benefits, and limitations. Let's start with what edge computing actually means. Edge computing is a distributed computing paradigm that brings computation and data storage closer to the data source rather than relying on a centralized cloud. It's a computing model where we bring processing power and data storage much closer to where the data is generated, like on the local devices, gateways, or nearby servers, instead of sending everything to a distant centralized cloud data centers. In simple terms, it's about analyzing and acting on data right where it's produced, which helps us save time, bandwidth, keep data more secure. Now, to make this idea clearer, let's think of a real life situation we can relate to. Imagine we are running a startup that needs financial advice for daily expenses and occasional investment. And here we are taking two cases. As you can see in the first case, every time, even for the smallest daily expense, we send all our questions and data to the big financial consultancy firm located in another city. They are experts. They analyze everything and then send back the advice we need. But because they are far away, it takes time, cost money to send all the data, and sometimes it's overkill for small day to day decisions. This is just like cloud computing. We send all raw data to remote cloud server, wait for it to process, and get the result back. Now imagine instead we hire an in-house financial advisor, for example, let a chartered accountant who sits right in our office. They can instantly handle all the small daily questions and only send the bigger, complex financial reports to the big consultancy. This makes decision making much cheaper and faster. And this analogy is just like edge computing, where processing happens locally first and only important or heavy data is sent to the cloud. So, just like having an in house advisor saves time and keeps sensitive information inside the office, edge computing saves bandwidth, reduces delay, and improves data privacy by processing data closer to where it's created. Now, let's move to why edge computing. We have cloud computing, but why is there need of edge computing? This technology increases the efficient usage of bandwidth by analyzing the data at the edges itself. In cloud, we require to transfer every data to the cloud and only then it will process and send the result. But in edge computing, it will only send large or complex data to the cloud. Instead, it will send regular data. Next point is it allows smart applications and devices to respond to data almost at the same time. And this decreases the latency which is in cloud computing. Then another one is it has the ability to process data without even putting it on a public cloud. This ensures full security because sensitive data doesn't travel over the internet to the public cloud servers. And at last, edge computing reduces the dependency on the cloud for immediate decisions while still using the cloud for large scale storage and analysis.
Today, I'll walk you through the evolution of the edge computing and how we went from the centralized system to the fast local processing that we rely on today. So let's begin with the very first stage of the computing, the centralized computing era from the 1950s to the 1990s. As the slide shows, in the early days of computing, everything was centralized. Think of it like as an all the brain power lived in a single giant machine, kind of like a mainframe in a locked control room. Exactly what you see on the image on the right. Those massive cabinets held all the power, while the device were just user device was just dumb terminals that they couldn't think for themselves. And as the second point says, that all the data was processed in those center servers, and then the people's devices has very little computing ability. Basically, they just followed orders. This was the time when computing was like a massive post office. You write your message, send it to that HQ, wait for them to process it, and then they'll mail back as a response. Slow, but it was the best that we had. Now, Moving on to the next slide, it is the rise of the cloud computings. In the 2000, we saw the rise of the cloud computing, which was a total game changer. As the slide says, cloud computing brought scalable, on-demand resources over the internet. Uh, Instead of just needing powerful machines of your own, you could now access computer power as a service from anywhere. Look at that image on the right. You'll notice a cloud platform sitting at the center, connected to the database and devices. This represents the platforms like AWS, Azure, Google Cloud, as mentioned in the second point. If centralized computing was like a single kitchen serving the whole city, then cloud computing was like the food delivery from the massive restaurants across the globes. You didn't need to cook the food, but you just ordered and got what you needed. But there was still one thing in common: process still happened far away in the centralized data centers. Then, moving on to the next slide, emergence of IoTs, and then came the 2010s, and with it, the explosion of IoT, the Internet of Things. As the first one says, billions of devices, from smartwatches to traffic lights, started collecting and sending data every second. If you look at that image on the right, you'll see people, devices, and icons connected to a massive IoT sign. This represents the massive data ecosystem. But now the cloud started struggling. As the second point points out, that the cloud couldn't keep up with the sheer volume of the IoT data, especially when the low latency responses were needed. This led to the third bullet, or the third point, the need of the decentralized processing closer to the source. This is where edge computing was born. Imagine, instead of just sending all the traffic updates to a central control room, we placed smart traffic officers at each intersection. They can make split-second decisions locally. That's what edge computing does. It brings intelligence right to the device or the edge of the network. Now, moving on to the next slide. Rise of edge computing, mid 2010s to onward. Now we move into the mid 2010s and beyond, where computer evolves yet again with the rise of edge computing. As you can see on the first point, edge computing took decentralization even further. It wasn't just about processing in the cloud data centers anymore. It was about processing right on the devices themselves, or at least very close by, at places like sensor routers or small on-site servers called micro data centers. This is what the term edge refers to. It is the edge of the network, right where the data is being created. So instead of shipping data all the way to the cloud, edge computing kept it local, which saved the time and bandwidth. So think of it like, instead of sending data or sending every ingredient to a distant kitchen to cook your food, you now have a chef in your own backyard, much faster and way more responsive. This became a critical for the time-sensitive application. As the last point says, we're talking about things like autonomous vehicles, where a delay of even few milliseconds could mean the difference between the safety and the danger, or AR, VR, industrial automation, and telemedicine, where fast local processing is absolutely necessary. So, edge computing is the reason that your smart car, smart watches can react instantly, or your wearable health devices can analyze your vitals in real time without waiting for the cloud. Now, on to the next slide. This slide contains a diagram that shows the architecture of the edge computing. The data is being processed closer to the source on the edge devices or nearby nodes, which is represented by layer 1 and layer 2, instead of being sent all the way to the cloud, which is represented by layer 3. This reduces the latency and the bandwidth use, enabling fast responses in the real-time applications like smart devices and autonomous systems.
So now let's understand the key components for edge computing. Edge computing relies on multiple key components to gather the data, to process it locally, and to transmit it between different devices. It first comes edge devices. Edge devices भनेको चाहिँ बेसिकली डेटा कलेक्ट गर्ने ठाउँहरू, जुन त्यो हायरार्कीमा सबभन्दा तल हुने पोइन्टहरू चाहिँ एज डिभाइसेस हुन्. अब दे क्यान इन्क्लुड सेन्सर्स, स्मार्टफोन्स, आइओटी डिभाइसेस द्याट प्रोभाइड्स डेटा टु बी प्रोसेस्ड. देन कम्स एज नोट्स. एज नोट्स चाहिँ अब हाम्रो जो सबभन्दा मेन कम्पोनेन्ट भनेर कन्सिडर गर्न मिल्छ. यसले चाहिँ त्यो एज डिभाइसले पठाएको इनपुट डेटा चाहिँ पाउँछ, अनि त्यसलाई चाहिँ त्यसले एकदम लाइट वेट प्री प्रोसेसिङ अथवा प्रोसेसिङ गरेर त्यसले इन्स्ट्यान्ट आउटपुट दिन सक्छ. अनि त्यसले अरू के पनि गर्न सक्छ भन्दाखेरि के लोकल डिसिजन मेकर भएर चाहिँ कुन चाहिँ त्यो ए सर्भरमा पठाउने, कुन चाहिँ क्लाउडमा पठाउने, अनि कुन चाहिँ त्यहीँ प्रोसेस गरेर अनि इन्स्ट्यान्ट आउटपुट दिनुको लागि गर्ने भनेर त्यसले त्यो पनि जस डिसिजन गर्छ. अनि त्यसले गर्दा चाहिँ हामीले जस क्लाउडमा रिलाइ नगरेर एकदम इन्स्ट्यान्ट रेस्पोन्स दिनु मिल्यो. अनि देन कम्स द एज सर्भर्स. Edge servers can be considered as specific edge nodes. They are basically more powerful than edge nodes in terms of computing. अब एज सर्भर्सले चाहिँ क्लाउडको कम्प्युटिङ लेभलसँग म्याच गर्न सक्छ कि यदि. अनि एज सर्भर चाहिँ जस त्यो एन्ड डिभाइसको एकदम नजिक हुन्छ. So the latency would be minimum if we are using a service to perform very high processing. अब लेभल म्याच क्लाउड कम्प्युटिङसँग लेभल म्याच भयो भने त जस त्यहाँ क्लाउडमा पठाउनै परेन हामीले त्यही ए सर्भर्समै हेभी प्रोसेसिङ गरेर त्यही नै रेस्पोन्स दिन मिल्यो। त्यसले गर्दाखेरि चाहिँ त्यो टु वे ट्रिप क्लाउडमा पठाउने अनि फेरि ल्याउने त्यो चाहिँ एकदम रिड्युस हुने भयो अनि त्यहाँबाट रियल टाइम झन् रियल टाइम जस्तो हुने हो। Then comes connectivity and network. If we are talking about a network with multiple devices, then connectivity is must. अझै हामीले अब लो लेटेन्सीको कुरा गर्ने भए त एकदम राम्रो कनेक्टिभिटी चाहिन्छ। त्यही भएर यो जस कनेक्टिभिटी चाहिँ हामीले राम्रो हुन्छ भने इन्स्योर गर्नुपर्छ। त्यसले गर्दा चाहिँ वी क्यान ह्याभ सिमलेस डेटा ट्रान्सफर्स बिट्विन एज डिभाइसेस, नोड्स, सर्भर्स, क्लाउड्स. And edge softwares are basically the softwares in the edge nodes or servers that do the processing like AI models. Also, they can be middlewares. They can be the middlewares that would be used to transfer the data between different devices. So now let's understand the workflow of edge computing. अब सबभन्दा सुरुमा डेटा जेनेरेसन हुनै पर्यो। अब हाम्रो एज डिभाइसेसहरू चाहिँ रियल टाइम डेटा ल्याउँछ अनि एज डिभाइसलाई पठाउँछ। अनि एज डिभाइसेसले चाहिँ अब मेन हाम्रो कुरा नै यही हो, लोकल प्रोसेसिङ एट एज। हामीले चाहिँ त्यो पाएकोलाई लोकली प्रोसेस गरेर एकदम इन्स्ट्यान्ट डिसिसन दिन सक्यौँ कि। त्यसले गर्दा चाहिँ जस रियल टाइम जस्तो फिल हुने भयो कि एकदम इमर्सिभ एक्सपिरियन्स हुने भयो। अनि त्यसपछि हाम्रो अब सब प्रोसेसिङ लोकली गरेपछि त क्लाउड खासै युज हुने भएन। त्यही भएर हामीले जस प्रोसेस गरिसकेको कुराहरू ओन्ली रिलेभेन्ट एन्ड समराइज डेटा वुड बी सेन्ड टु द क्लाउड लाइक फर स्टोरेज एन्ड अदर मल्टिपल थिङ्स। अनि हामीले चाहिँ इफ वी डोन्ट ह्याभ ए सर्भिस वी क्यान युज क्लाउड टु डु द टु टु डु द हेभी प्रोसेसिङ। अब ए सर्भिस नभएपछि त्यो इज नोट्सहरूले चाहिँ अब के लजिकल डिसिजन बनाएर चाहिँ उसलाई पठाउँछ अनि क्लाउडले चाहिँ हेभी प्रोसेसिङ गरेर दिन्छ, फिगर दिन्छ। अब यो फिगरले चाहिँ जस हामीलाई बेसिकली भिजुलाइज गर्न हेल्प गर्छ। अब तल चाहिँ एज डिभाइसेसले चाहिँ एज नोडलाई पठाउने भयो अनि तिमीले प्रोसेस गरेर फेरि एज डिभाइसलाई पनि पठाउने भयो अनि तिमीले फेरि क्लाउडलाई पनि पठाएर त्यहाँ स्टोरेज गर्नु अथवा हेभी प्रोसेसिङलाई क्लाउडलाई पनि दिनु भयो अनि क्लाउडले पनि एज नोड्सलाई फेरि त्यो डाटाहरू दिने भयो। यो चाहिँ बेसिकली हाम्रो वर्क फ्लो भयो।
Hi everyone, I'm Prashesh Adhikari. Uh, Now that we have explored how edge computing works, let's look at where it's making a real impact in today's world across several industries. First, let's talk about autonomous vehicles. Self-driving cars are one of the most exciting applications of edge computing, and these vehicles rely on a huge range of sensors, including radar, lidar, and high-resolution cameras that generate an enormous volume of data every second. To navigate safely and avoid collisions, this data has to be processed instantly. There's no time to send it to a cloud server and wait for instructions. That's why the vehicle's onboard computer acts as the edge processor, handling everything from obstacle detection to lane positioning in real time. Edge computing here is not just a performance boost; it is a life-saving necessity. Now, let's look at healthcare. Edge computing is playing a growing role in telemedicine and remote patient monitoring. Wearable devices like smartwatches or medical grade sensors can now track vital signs such as heart rate, oxygen levels, or blood pressure continuously. These devices often connect to a local edge processor, whether it's a smartphone or a nearby gateway, which can analyze the data and trigger alerts instantly if something seems wrong. This is especially powerful in rural or remote areas where cloud access may be unreliable. Finally, telecommunication. As we move on in the 5G era, edge computing is becoming a backbone of telecom infrastructures. By placing edge nodes closer to users, telecom providers can offload network traffics and reduce the distance data must travel. This doesn't just make the network faster; it enables new technologies like virtual reality and real-time gaming, all of which demand ultra low latency. Now let's come to key benefits of edge computing. We have already discussed real life applications of edge computing, so we can deduct key benefits of edge computing from there as well. Now, first of all, faster response time, because data is processed right where it's generated on the device or a nearby edge node. We eliminate the need to send everything back and forth to the cloud, so it gives faster response time. Improved security and compliance. With edge computing, data can stay local, reducing exposure to external threats. This is especially valuable in sensitive sectors like healthcare or finance, where keeping data close helps meet privacy regulations and security standards. Cost-effective solution. Edge computing significantly reduces bandwidth and cloud storage cost. By filtering and processing data locally, we only send what's necessary to the cloud, which means lower data transfer fees and less demand on centralized infrastructures. Reliable operation with intermittent connectivity. Edge computing allows devices to keep functioning even without internet access. This is especially important in remote areas, in transit, like on a train, or during network outages. Devices continue collecting and analyzing data and sync with the cloud once reconnected. Reduced latency. Finally, edge computing minimizes the delay. Finally, edge computing minimizes the delay between data capture and action. This is essential for time sensitive systems like robotic surgery, automated machinery, or real time fraud detection, where every millisecond counts. So, this were some of the key benefits of edge computing. Uh, Now, let's talk about the limitations of edge computing. First of all, we have complexity. Setting up and maintaining edge computing systems can be challenging, especially if there are many devices or a vast geographical region involved. Limited resource is one of the limitation of edge computing. Edge devices, edge software, edge nodes frequently have constant processing, storage, and bandwidth, which can restrict their capacity to carry out specific activities.
So another limitation of this edge computing is dependence on connectivity. So in order to for edge computing to work correctly, connectivity is required. So what it means is that the network devices that are connected into the network must be connected at a common network for them to work effectively under the system. So otherwise, if they are not connected properly, then the data transfer might not happen between them, and or in the worst case scenario the whole system might crash. So it is one of the limitation of the edge computing. So next limitation is security concerns. So edge devices may be susceptible to security risks such as malware, hacking, and physical interference. So what it simply says is that the edge system or edge computing system is not specially designed for any kind of security related issues. So that it means that it is equally prone as the other systems for hacking and other kind of malware attacks. So moving forward, the topic is about future of edge computing. So what simply is the future of edge computing is that the edge computing is a rapidly transforming niche solution into a foundational pillar of modern digital infrastructure. So, as any technology evolves, there might be the demands that emerge in the upcoming future, and similarly, the edge is expected to play the similar critical role in the shaping the future of data processing, connectivity, and automation. So, if there is the room for future enhancement, then there are some areas where the future enhancement must be required in the upcoming days. So one of the major area for future enhancement in edge computing is AI. So what actually is AI is the integration of artificial intelligence directly on the edge devices. So whenever the different algorithms and training tasks needs to be done on edge devices, then this edge AI is the place where the integration of artificial intelligence helps to run the different kinds of tasks and related to artificial intelligence effectively on the edge devices. So its impact is that the real-time decision making without any cloud dependency enables smart surveillance, facial recognition, and predictive maintenance. So the next area of edge computing is 5G and beyond the 5G. So what 5G actually does is there are different kinds of capabilities that comes under 5G. So one of them is enhanced mobile broadband, ultra reliable, low latency, and so on. So
5G basically provides the real-time communication for applications like autonomous vehicles, smart cities, and AR VR, enhance mobility and scalability of edge devices. Future outlook: the edge and 5G will evolve together to support 6G, which is beyond the 5G and next generation working. So beyond 5G, there are AI native networks and tetrahertz of frequency of spectrum. So it supports 5G and beyond that. So next one is edge computing for metaverse. So metaverse is basically the big platform where low latency, high responsiveness, and spatial awareness are critical. So edge devices must be able to handle the tasks like 3D rendering, AR, VR tracking, and real world interaction without relying on distant cloud servers. So edge computing might work and become handy in this scenario of metaverse. So impact is that it enables spatial computing, digital twins, and smart environments, and it is fast enough to get response to gestures, voice, motion, and which is critical for immersion. So by saying this, I want to conclude this presentation on behalf of my teammates. So thank you this much for today.